So the next talk will be by Professor S.Kesavan. As you know, he's a master in, he's an expert in partial differential equation. He's a faculty member here. And he'll be talking on from the triangle inequality to isoperimetric inequality.
Good morning. So thanks to the organizers for asking me to speak here. The topic which I am going to discuss today is just this opening of a small peek into what is called calculus of variations. You routinely do and teach maxima, minima of functions in one variable. And in your master's courses, you must have studied functions of several variables, where you do maxima, minima of functions of 2 variables, 3 variables, n variables, and so on. Calculus of variations is something you can very crudely describe as maxima and minima in infinite dimensional vector spaces. And it's an important part of this because this always happens in physics and engineering, because nature always tries to, this principle of least action. So nature is always trying to minimize its efforts. And another important area is what is called shape optimization. So whether you want to build an airplane, a car, or a machine part or something like that, it has to do some job, and then you choose amongst all possible shapes the best shape which will serve your purpose. And all this involves some kind of optimization, or that is finding maxima or minima in an infinite dimensional vector space. Today what we are going to look at is something very, very simple, using just high school geometry, which we will see how far we can go. Okay? And starting from a very simple theorem, we will end up in a fairly deep theorem in the So one of the important results we learn in plane geometry at high school is that in any triangle, the sum of the lengths of any 2 sides is greater than the length of the third side. So this is called the triangle inequality, and it has been generalized as the triangle inequality when defining a metric which generalizes the notion of a distance in topology and plays a very key role in the study of metric spaces. A particular case is the inequality bearing the same name when defining a norm on vector spaces. Anyway, all this is just as aside. It has nothing to do with what we are going to do. So now what's the first problem of this kind? Given 2 points A and B on the plane, what is the shortest path from A to B? Straight line joining them, right? So have you seen a proof of this? How do you prove that the straight line is the shortest path from A to B in the plane? So let's see how we are going to do that. So a polygonal path is a path joining 2 points which is made up of line segments. So you can have a typical example, A to C, C to D, D to E, E to B. So that is a polygonal path. So in this figure, from the triangle inequality, you have that AB is less than AC plus CB, right? Similarly, CB is less than CD plus DB, and DB is less than DE plus EB. So you add up all these, you get AB is less than AC plus CD plus DE plus EB. So if you walk along this polygonal path, the distance is much more than going straight from A to B. Now you can generalize this using mathematical induction to any number. So of all possible polygonal paths joining 2 points in the plane, the straight line has the shortest length. This is just a direct consequence, corollary of the triangle theorem. Namely, 2 sides of a triangle is bigger than the third side. Okay. So what is a curve? A curve is nothing but a continuous function, gamma, from say a finite interval 0, 0, 1 into the plane. The endpoints of the curve are gamma naught and gamma 1. These are points in the plane. And the curve is said to be a simple curve if it does not intersect itself. That means this function is a one-to-one function or injective function. and it is said to be a closed curve if it comes back to the starting point. So, gamma 0 equals gamma 1. So, you move from 0, 1, gamma of t traces something like what Revati showed today. It traces a path, the thing. If it does not come and cut itself in the middle, then it is called a simple curve. Other than if it comes back to the starting point like an ellipse or a circle and so on, that is called a closed curve. Now, how do you define the length of a curve? Okay, if it's a nice smooth function, then you probably have taught in your calculus classes some formula, integral is square root of 1 plus y dot square, etc. But in a general, continuous function may not be differentiable, and therefore, how do we define? So, starting from the time of Archimedes, we have been doing the same thing. We take a partition of the interval, and then each point gamma ti as at each partition point gives you a point on the curve. And now you join consecutive points, you get a polygonal path, you get a straight line, okay? And then, so let LP denote the length of that polygonal path. So you have a curve, so this is my first point, this is the end point. Now I mark off some points here and then join these by straight line segments. So I get a polygonal path, and that path I call L of P as the length. Now the definition of the length of the curve, a curve is said to be rectifiable. That means rectifiable means I can define the length of a curve. There are not every curve you can define the length. For instance, fractals are typical examples for which you cannot define the notion of a length. So a curve is, you can define its length if the supremum of all these polygonal lengths is finite. Supremum is a least upper bound, okay. So if the supremum of all, if you take all possible partitions, then take the corresponding polygonal paths, take the total length, and then take the supremum over all possible partitions, just as you define Riemann integral and so on, okay. Then that is called the length of the curve. So from what we have said, the straight line length is less than the length of any polygonal path, and therefore it has to be less than the supremum also. So given any curve from A to B, the length of the curve will definitely be bigger than the length of the straight line. So this is a proof using just elementary geometry of the fact that the shortest distance from A to B is a straight line, because the straight line is less than any polygonal path, and the supremum of all polygonal paths is the length of any curve, and therefore every curve will definitely be longer length than the straight line. Okay. Now let us look at a little different. So this is a first problem in calculus of variations. You have so many possible ways of going from A to B, and you have asked which is the shortest, okay. So this is the example of a problem in calculus of variation. So now let us look at a different problem. Consider 2 points A, B in the plane and a line L lying below them. Consider all possible paths from A to B such that which is made up of two line segments AP and PB, where P lies on the line. So we have a line here, and I want to go from A to B, but I don't want to go like that. I want to touch this line and then go. And I'm asking what is the shortest path I can take. Imagine that there's a horseman who has been riding all day. He has arrived here, and the stable is here. So the horse has to be taken to the stable, but it's very tired, so it needs a drink of water. And so there's a river here. So he has to first take it for a drink of water and then go back to the stable. And since the horse is very tired, he doesn't want it to walk too much now, and therefore he is looking for the shortest possible such path. So how do we solve this problem? Well, if it were just directly from A to B, we know we have to take the straight line. But now I have given you a constraint, namely I have to first come to this line and then go. So how am I going to solve that? So what I do is I take the reflection of A on this line, call that point A1. Then these two triangles AOP and A1OP are congruent. You have a common side, you have right angles here, and these two are equal because of the reflection. Two sides and included angle, and therefore you have AP equals A1P. So AP plus PB is the same as A1P plus PB, right? So the distance of any admissible path from A is the same as the distance of any path from A1 to B. And you know what is the shortest path? It is the straight line, because now anyway I will cross, so it doesn't matter. So the red line here gives you the shortest path from A1 to B, and therefore the shortest path from A to B will be the reflection of that. Now let's look at that. So those two triangles are still congruent. So these two angles are equal, vertically opposite angle. So 90 minus that, so these two angles are equal. So the shortest path is got when the angle of incidence is equal to the angle of reflection. Okay.
So I'm wondering, so what could be the definition of a straight line? Because I'm wondering whether
that's part of the Euclid axioms, right? We know what the point is, what a straight line is. I mean, the
straight line is an axiom.
Yeah, I mean, it's part of that. I mean, a straight line is that, or if you want to define in terms of an equation, give coordinates and do it.
No, my concern is.
So what's a point? Okay, what's a point? What's a straight line?
No, my concern is. Maybe I don't know whether maybe we'll be going in loops. Maybe finally we'll define the shortest path as straight line or something. I don't know.
No.
So I'm wondering, is there a proper definition or for straight line? But again, distance is, you need to know a notion of length for distance. So I don't know, I'm wondering.
Okay, so if you, so then how did we define a triangle then? Okay, so let's, maybe we should discuss that some other time, okay? Fine. So this shortest path is got by when the angle of incidence is the angle of reflection, and this you have seen also in the laws of physics. So in fact that is called Fermat's principle. Fermat's principle says that light always takes the shortest possible path, and that is why the law of reflection obeys this thing. And if you have two different media, you can derive the law of refraction also from this principle. Okay, so that is Fermat's principle. Now let us look at another problem. Okay, this theorem is called Heron's theorem, which says that the shortest path is when you have this, what we have. So as an exercise, you can try this. You have two lines, LL1 and MM1, and 2 points A and B between them. And now I want to take paths A to B, but which first touch L line, then goes to the M line, and then goes to B. So find out how will you locate the shortest path using the same principles. Okay, so this is a simple exercise based on what we have just seen. Now we look at some optimal triangles. So let A and B be fixed positive constants. Amongst all triangles ABC with base length fixed as B and area fixed at A, we look for a triangle such that AB plus AC is the least possible. Okay. So again, so let us say there's a highway here and the government has decided from here to here we will construct a park. And the park will be triangular in shape and you are given 1 acre of area, that's all. So then we are interested in finding a triangle such that the sum of these two sides is as low as possible so that the cost of constructing the fencing or the compound wall or painting it or whatever is going to be the least. So we are looking for all possible triangles ABC such that BC is fixed, the area is fixed, A alone should vary. And how should we choose the point A? vertex can only move on this line. If all triangles of the same area and the same base, the vertex will have to be forcibly on this line. Now, this is a problem which I have just solved. So, I am looking for paths from B to C touching this line L and which is shortest. This is just the previous theorem, and it says that it will do so when the angle of incidence is equal to the angle of reflection, and which means this triangle BA0C is what? Isosceles. Okay. So, we have proved the following theorem. Of all triangles with fixed base and fixed area, the isosceles triangle minimizes the sum of the lengths of the other two sides. Okay. So, these are the kind of shape optimization problems which these things throw up. Now, when you do maxima minima problems with constraints, there is always a notion of a dual problem. Suppose I have maximize f of xy, say, in two variables, such that g of xy equals constant. This is a typical kind of constrained optimization problem which you get. This is the condition, this is the constraint. Subject to this, I want to maximize f of xy. Then there is a dual problem which says minimize g of xy such that f of xy is a constant. Now, the nice thing is both of these have the same answer. The maxima of the first one or the minimum of the second one will generally occur at the same point subject to some conditions. So, one problem may be easier than the other, or both may be difficult, both may be easy, I do not know. Just like Tyagaraja said, Dvaitamu Sukama, Advaitamu Sukama. So, you do not know which. So, this typical duality is a very important notion in mathematics. So, you have a dual problem. So, what is the dual problem here? Of all triangles with fixed base length and fixed sum of the lengths of the other two sides, find the triangle with maximum area. So, earlier we fixed the sum of the other, we fixed the area and minimize the sides. Now, we fix the sum of the sides and maximize the area. Answer should be the same. So, it should be again the isosceles triangle. You can do it as an exercise directly to show this. I will quickly tell you what it is. So, you draw the line LL1, the isosceles triangle, okay, where the and then any point P here, we just saw BP plus PC will be more. So, if this isosceles triangle has the prescribed total sum of the other two sides, this will all have more, and so they will not qualify. If you take any other line so that the area is more, these will definitely be more than the sum of these two sides. So, again they are not going to qualify. So, if you want to have the same sum of the other two sides, you must look for a vertex in a line lower, which means the area is lower. So, the maximum area is only got by the isosceles triangle here. You can give another proof of this. So, of all triangles with fixed base length and such that the sum of the lengths of the other two sides is a constant, the isosceles triangle has the maximum area. Those who know conic sections, of course, this is a very simple proof. If B and C are fixed, Revati just now told you that if points which moves is that it's sum of the distances from B and C is a constant, is a ellipse, okay, and B and C will be the foci of the ellipse, and therefore the semi-major axis is given by 2a equals L, and the eccentricity of the ellipse is given by BC equals 2ae, and the semi-minor axis is then defined by b square equals a square into 1 minus e square. So, if O is the origin which is the midpoint of BC and theta is the angle which the ray OA makes, then the coordinates or A cos theta, B sin theta, you know. So what is the area of the triangle ABC? Half into BC into B sin theta. When is this maximum? When theta equals pi by 2. That means the A must be on the minor axis, which means you have an isosceles triangle. Because you have BC, midpoint of BC is the origin, and the minor axis is therefore perpendicular bisector, and therefore you have an isosceles triangle. So this can also be proved using conics, or as I said, directly by geometry, or from the previous theorem, the fact that a problem and its dual problem have the same answer. So now we look for isoperimetric problem for polygons. Iso is a Greek prefix which means same. If you have isotopes, topos is location, so they have the same location on the periodic table. That's why they are called isotopes. Isomorphism, same structure, so you have seen that in chemistry or both mathematics. Isobars, same pressure, isotherm, same temperature. So we are looking at isoperimetric. That means we are looking at figures whose perimeter is the same. And then we are trying to do the maximum or minimum of something. Okay. So we look at the following problem. Of all n-sided polygons with the same perimeter L, find the polygon which encloses the maximum area. So this is the problem, shape optimization, which I am going to try. So let us look at triangles. So n equals 3, so we are dealing with triangles. So L is the perimeter of a triangle of sides ABC, then L can be 2S, which is A plus B plus C. S is the semi-perimeter. Then you have Heron's formula, which gives you the area of the triangle, which is square root of S into S minus A into S minus B into S minus C. So L is fixed means S is also fixed, because S is nothing but L by 2. Okay? So if I want to maximize A, I just have to maximize S minus A into S minus B into S minus C, because the square root is nothing. If you maximize some number, its square gets maximized automatically. Now the sum of these three numbers is 3S minus A plus B plus C, which is S, and that's also a constant, L by 2. So we have three positive constants whose sum is fixed, and you want to maximize the product. And this is the famous arithmetic geometric mean inequality, because AM is greater than or equal to GM, right? So this is the AM GM inequality for any n you have this. So x1, x2, x3 is always less than or equal to x1 plus x2 plus x3 by 3 whole cube. This is the maximum value you can attain. And when will you attain this value? Yes? When all the three are equal. That is when? Yeah. So S minus A must be equal to S minus B must be equal to S minus C for the maximum, which means A equals B equals C. That is, the triangle has to be equilateral. So of all possible triangles with the same perimeter, the equilateral triangle will have the maximum area. Okay. Now let's look at quadrilaterals. So we want to look at all quadrilaterals with fixed perimeter and see if we can identify the one which has maximum area. Again, the answer was when you dealt only with rectangles. She demonstrated this morning that you got a square, right? That was one of the demonstrations earlier today. Okay. First of all, it is enough to have convex quadrilaterals, because suppose I have a dented quadrilateral like this, A, B, C, D. then I just take a reflection of these two sides on this line. So I get a new quadrilateral ABCE. Now the perimeter of ABCD and ABCE are the same because AB and BC are common. AD equals AE, DC equals CE. So the perimeter has not changed, but the new quadrilateral encloses larger area. So you can, it's enough to look at convex quadrilaterals. You don't have to look at dented quadrilateral, non-convex. Okay, so now let us start with a convex quadrilateral, ABCD. Now I am going to do something. I am going to keep BD fixed and replace BAD by BPD, which is an isosceles triangle, such that sum of these two sides is the same as sum of these two sides. Okay? Similarly, I will keep BD fixed and replace BCD by BRD such that it is an isosceles triangle and sum of these two sides is equal to the sum of these two sides. Then have I changed the perimeter? Perimeter is still the same. What about the area? It has increased because if you fix the base and fix the sum of the other two sides, we just saw that the isosceles triangle had the largest area. So the area of this upper triangle is bigger than this one. The area of this lower triangle is bigger than this one. So the area of this quadrilateral is definitely bigger than this, keeping the perimeter same. Now I play the same game again. I take PR and replace this by an isosceles triangle, keeping the sum of these two the same. I replace this by an isosceles triangle, keeping the sum of these two sides same. And now what happens? Because these were already isosceles here, so this becomes a rhombus now, because all the four sides will have to be equal. And this area is bigger than this area. This area is bigger than this area by the same theorem. Base is fixed, sum of the two sides is fixed, therefore maximum area for the isosceles triangle. So given any convex quadrilateral, I can construct a rhombus with the same perimeter but which has larger area. So now if theta is the angle, internal angle of the rhombus, what is the area of the rhombus? It is L by 4, which is the side of the rhombus now. L is the total perimeter, L by 4 is the side times sin theta, and that is maximum when theta is 90 degrees. So that means of all possible quadrilaterals, the square has the maximum area. Not just rectangles as it was shown this morning, but you take any quadrilateral, fix the perimeter, then the square has the maximum area. So for triangles, it was the equilateral triangle. For squares, quadrilaterals, it's the square. So what do you think is the obvious answer for the n-sided? Regular polygon. Okay. So of all n-sided polygons of fixed perimeter, the regular polygon encloses maximum area. By a regular polygon, we mean one which has all sides of equal length, that's an equilateral polygon, and whose vertices lie on a circle. Okay, you can have equilateral polygons like rhombus, which will not lie on a circle, okay, but the square alone will lie on a circle. Okay, so this proof is of course nowhere simple like the geometric proofs which we have seen up to now. So it requires some other techniques. We will prove, or at least give a type proof, in the case when you have two n-sided, namely even-sided polygons, not anything. And you will see why I want even side in a moment. So the proof of this is involved, and we will present here an ingenious argument due to Steiner for polygons with even number of sides. Up to now, we have to now change our tactics a bit. Up to now, the triangles and quadrilaterals, I directly produce the maximal element and I proved that it is maximum. I showed that the equilateral triangle is maximal. I showed the square is maximal. Now I cannot do that. Okay. So we have this optimization is always a two-step process. First, we have to show that there is an optimal solution. And secondly, we have to identify that optimal solution. Now, if you took a function of one variable, for instance, your class children will immediately put f dash equal to 0. Now, that is not the end of the story. Okay? It requires a further test whether it is a maximum or a minimum, or if you took horrible functions like y equals x cubed, you will get f dash x equals 0 at the origin, but that is still nothing to, it is neither maximum nor minimum. So, you have to show first of all there exists a optimum and then identify. The identification problem is usually easier because you have some technique to do it, like finding the zeros of the first derivative. Okay. So, here also we have to show first of all that there is an optimal polygon at all, and secondly we have to identify it. Okay, the first one I want, it involves some amount of topology, but it is not very difficult. It just depends on the following fact: continuous function on a compact set attains its maximum and minimum. Okay, so that's all. That's the only thing which you must know. But let us not bother about that proof. We will assume there exists an optimal polygon and we will identify it. Okay, so now I have skipped the proof of the existence of an optimal polygon. I am assuming it. So now we are going to identify it as the regular polygon. Okay. So first of all, we take the optimal polygon and look at any pair of arbitrary sides, arbitrary pair of sides here. Now I freeze all these other vertices and I allow B alone to move. And how will I allow it to move? I do not want the perimeter to change. So AB plus BC must still be a constant, so that the total perimeter is not changed. I am just moving this vertex B to create new polygons. Okay? Other vertices of the optimal polygon are frozen. So this alone is allowed to move, and in such a way that AB plus BC does not change, and therefore the total perimeter is still the same. But then what do you know? So the area of the polygon can change only by changing the area of this triangle. And when is that maximum? When you have an isosceles triangle. We have seen this. So AB must be equal to BC in the optimal polygon. So in the optimal polygon, any pair of adjacent sides have to be equal. That means all the sides have to be equal. That means it is an equilateral polygon. Now we have to show that all the vertices lie on a circle. So that is the next problem. Yeah, this is what I was just saying. So now let me draw, there are two n sides. So this is why I am taking 2n now. We have 2n sides. So let me draw a diagonal of this polygon so that there are n sides on one, n sides on the other. So the perimeter has been bisected because it is now an equilateral polygon. All the sides are equal. I have n on one side, I have n on the other. So the total length of on either side is the same, and so I have bisected the perimeter. But the miracle is I have also bisected the area. Because suppose the top had more area than the bottom, simply reflect it. Now I create a new polygon which is bigger area than the original one, which is not possible because I am dealing with the optimal polygon. Optimal polygon means it has the largest possible area for that perimeter. And therefore, if you have an optimal polygon, take any diagonal bisecting the perimeter, it will also automatically bisect the area. And so from now on we will now work only with half of the polygon, because I can always reflect it to get the other half. Okay. So that is why this argument works only for even sided polygons. So this is a half of the optimal polygon, and I am going to allow it to make some changes. How? I fix, this is the diagonal which bisected the perimeter and the area. So these are the two vertices A and B, and I take any arbitrary vertex. Now I freeze everything else. So I allow PA and PB to change by sliding A and B on this line. A and B are allowed to slide on this line. Nothing else is allowed to change. So it is a rigid body motion. So this is fixed, this area is fixed. All these sides, they just undergo some sliding motion. So A and B alone will move along this line. Everything else is fixed. So the perimeter does not change for any of these polygons. Only the area changes. And the area, how is it changing? This is not allowed to change. This is not allowed to change. The only thing which changes is this area. And what is that area? Area of a triangle is half times PA, PB into BC sin A, no? Half BC sin A, that is famous. Okay. So half of PA into PB into sin theta, that alone will change. So we change the area by moving this, and so the area is half PA PB sin theta, that is the only one which is changing. And when is that maximum? When theta is 90 degrees. So going back, when the optimal polygon, this angle theta must be 90, and it does not matter which vertex I do, every time it has to be 90. That means all the vertices subtend 90 degrees on this diameter, and therefore they all lie on the semicircle with this as the diameter. So the optimal polygon has to be the regular polygon. So now we know, given any polygon of 2n sides, the optimal polygon is the regular polygon of the same perimeter, okay, lying on, with vertices lying on a circle. So let us take a polygon whose perimeter is L and area is A, then it is a 2n sided polygon. Then you consider the corresponding regular polygon with the same perimeter. Then each side will have length L by 2n, because there are 2n sides, they are all equal, so it has to be L by 2n. The angles subtended at the center of the circle, they all lie on a circle, right? The vertices lie on a circle. So the angle subtended at the center is pi by 2n.
Could you repeat the earlier statement? How did you say it is a circle?
How did I say?
How did you conclude that it is a circle?
Yeah. See, this angle I showed has to be 90 for the optimal polygon. So whatever may be the vertex, AB subtends an angle of 90, that means they all lie on the semicircle with AB as diameter. And that is half your polygon, the other half will be got by reflection.
So my question was, so there is this theorem called where it says in a semicircle angle is 90. So I was wondering the converse is also
true, because you take the midpoint of the hypotenuse, okay, and that okay. So the length angle subtended at the center is 2 pi by 2n, which is pi by n, and so half of that angle is pi by 2n. So then I can compute the height of this. This is half of this is L by 4n by h is tan of theta, okay, from which I can get the height. So, the height of is L by 4n by tan pi by 2. Okay. Is this correct? The height of the triangle. Here you have a right angle triangle. This is L by 4n divided by h is tan of theta, which is pi of 2 by n. So, h is equal to L by 4n divided by tan something. So, the area of the triangle is half base into height again. So, that is L square by 16n square into 1 by tan pi by 2n. And how many triangles are there? 2n triangles, because it is a 2n sided polygon and I have joined it each vertex with the center, I get 2n triangles. So, the total area of the regular polygon is L square by 8n times 1 by tan by 2. Okay. So, this is
maybe you are going to set n tends to infinity.
Yeah. That is what I am going to do.
It does not matter whether it is really 2n or something.
Yeah, it does not, but so I only identified the theorem is true for any n, as I said. The optimal polygon is the n-sided regular cyclic polygon. Okay. Now, for 2n I gave you an argument. For n it is not easy. For odd n I cannot give a geometric argument. I need to do some analysis to do that. Okay. But for 2n elementary high school geometry argument is there, which you can convince your class children easily. That is all. It does not matter whether n is odd or even, but since I am working with even, so I am continuing on that. So, this is the total thing. So, now we have the following nice theorem. If L is the perimeter of any two n-sided polygon and A is its area, since I know that A is less than the area of the regular polygon, which is given by L square by 8n in this fashion. So, A is less than this. Okay. So, I cross multiply, I get L square is greater than 8na tan pi by 2. Okay. So, take any two n-sided polygon, this theorem is true. If L is the perimeter and A is the area, and n is 2n is the number of sides, then this inequality always holds. Good. So, now let us take a curve and mark off two endpoints on the boundary and join up these things. So, let Ln be the perimeter of this polygon and An be the area. Then we just saw that Ln square is greater than 8n An tan pi by 2n. This inequality was just proved. I am going to rewrite it in a different way. I will write it as 4 pi An tan pi by 2n divided by pi by 2n. This manipulation. Now, as n tends to infinity, I can choose these points on the boundary such that this length of the polygon converges to the length of the perimeter of the curve and the area converges to the area. This is how Archimedes computed the area of the circle and such things. Okay. So, now we will let n tend to infinity. So, Ln square will go to L square, An will go to A and 4 pi is there. Now, this is tan theta by theta as theta tends to 0. So, it goes to 1. So, we have now proved a very deep theorem which says that if you have any simple closed curve in the plane, if L is its perimeter and A equals area, then L square is always greater or equal to 4 pi A. Okay. So, this is a very This is known as the classical isoperimetric inequality. So, whatever may be the domain you have, if L is the perimeter and A is the area, then L square is always greater or equal to 4 pi. And equality occurs for the circle. Namely, if L is 2 pi r and A equals pi r square, then L square equals 4 pi A. And you can prove that's a little more complicated. You need some Fourier series arguments or some other arguments for this to show that if L square equals 4 pi A, the curve is necessarily a circle. No other curve will achieve this. That is another beautiful result, but that's more complicated to prove. The proof of this is easy just by geometry, but that requires some more analysis. Okay, so the only curve which achieves equality in the isoperimetric inequality is the circle. Okay, now what does this mean? This means the following. Rephrasing it, if L is the perimeter of a simple closed curve, then the maximum area it can enclose is L square by 4 pi. And if A is the area enclosed by a simple closed curve, then the perimeter should be at least square root of 4 pi A. It can't be more, it can't be less than that. Okay? The circle alone achieves these optimal values. So let us rephrase this again. Of all curves of given perimeter, the circle encloses the maximum area. Of all, so the dual problem, of all curves of given area, the circle minimizes the perimeter. Okay? This is the dual problem. You maximize one, keep the other constant, or minimize the first one, minimize the second one and keep the first one constant. Okay? So this says that of all curves in the plane which have the same perimeter, the circle maximizes the area, and of all curves in the plane which have same area, the circle has the least perimeter. Yeah, so that is what I have said. You know, one thing about maths is nothing goes out of fashion. So this problem is as old as the hills. It is mentioned in Virgil's Aeneid, okay, which is Greek mythology, Latin literature and so on. So in Virgil's Aeneid, this is known as Dido's problem. Dido was a princess, a Phoenician princess. She was driven away from her country by her brother. So she crossed the Mediterranean with some followers and landed in North Africa in a place which is today Tunisia. In olden days it was called Carthage. Okay, you must have studied about Hannibal of Carthage and all that. Now, this Dido wanted to form her own kingdom in this new place. For that she needed to buy some land. So she wanted some land. But the local tribes people, they didn't want to give her much land. So they said, okay, we'll give you so much as you can cover with a piece of ox hide. They thought they were being clever, but she was cleverer. She interpreted the enclosing by a piece of ox hide in a different way. They thought she will just put it like that. No, she cut it into fine ribbons, tied them all up in a rope. Now she had a rope of fixed length. Her problem was to put it on the ground in such a way that the area was maximized. And that obviously is the circle. Okay, of course, she did it on the seashore, so she had to put it in a semicircle because she had the sea on one side. Okay, so this is called the Dido's problem, and it's as appears in Virgil's Aeneid. Okay, and this is the first known instance of an isoperimetric problem or shape optimization problem in history. Now there is no sanctity about 2 dimensions in all this. So even in 3 dimensions you have a similar inequality. So you take any volume, let S be the surface area and V be the volume. Then you have the inequality corresponding to L square greater or equal to 4 pi A you will have S cubed greater than or equal to 36 pi b square. So you can go home and try, take a cone, cylinder, prism, whatever you like, any object whose surface area and volume you can compute, plug in these two values, you will find that this inequality is always true. And of course, equality holds for the ball. S surface area is 4 pi r square, volume is 4 by 3 pi r cubed, and therefore you will have equality. And again you can show, and it is far more difficult than the previous case. In 2 dimensions, at least Fourier series helped us to do it. Here it is even more tough. You need some work to do with partial differential equations, and there you can show that in fact if you have equality, then it has to be a ball. So only the ball. So how do you interpret this as shape optimization problem? Of all 3-dimensional bodies with fixed volume, the sphere alone has the least surface area. Of all 3-dimensional bodies with given surface area, the sphere has the maximum volume. These are the 2 dual problems which you are looking at. And this has a very nice application. So when you blow a soap bubble, it will wobble a bit and then settle down to a nice ball and fly away. Why? Because the soap film is a liquid and it is in a liquid air interface, and that means there is surface tension, and physics tells you that for stability surface tension has to be minimized, and surface tension is also directly proportional to the exposed area. So when I blow a soap bubble, I blow a certain volume of air according to my lung capacity. Now nature has to adjust the shape such that the exposed surface area is minimum, and that is the ball.
So a drop of water also becomes a spherical droplet.
Yeah, because of the surface tension. Okay. So nature chooses this most beautiful symmetric shape, not because it was symmetric, but because it satisfied this problem, namely it minimized the surface area, which minimizes in turn the surface tension, and therefore the soap bubbles are going to be. You can write the isoperimetric inequality in n dimensions also, but anyway. Yeah, this is what I just said. So isoperimetric inequality is the starting point of a subject of shape optimization problems, where we look for shapes which optimize some functional subject to some geometric constraints. Okay, so this is general. So in this case, we maximize the volume, fixing the perimeter, maximize the area, maximize the volume, fixing the surface area, something like that. So you fix something and you maximize or minimize something else. Okay.